Right? Mark, the floor is yours.
Okay, great. Hi everyone. My name is Mark LeAir, and I'm one of the compiler engineers for NVIDIA that's working on the Flang compiler. And today I'm going to give a code walkthrough of an intrinsic implementation. In particular, we're looking at the fur lowering, which is going to be the lowering from the front end into the MLIR that the compiler backend will then be able to generate the code for. Couple preliminary things is that there is a tutorial. Some of you probably have seen it already. That going to have a little more detail than what I'm going to present here today. Even some information on implementing the intrinsic from the front end all the way through the back end. And what I mean by that, to the runtime library. That's what I mean by that. So I would encourage you guys to take a look at that as well. I'm going to put the link in the chat here. So I'll put that link right now into the chat. The other thing in the chat is there is a link to a GitHub issue that where we're putting intrinsics that are needed for F95 compliance, and people can sign up for them there. There's also a spreadsheet that's out there. I don't know if I don't believe any. I don't know if everyone can get access to it or not. But if you talk to Steve Scalpone about if you want access to it, I think we could maybe make that happen. So that's the preliminary things, and then in terms of what we're going to accomplish here, this is my terminal, and it is a GitHub clone of the F18 project, in particular the FurDev branch. And so what we've been doing is we've been working with a branch of the project and called FurDev. So you can, in fact, you can see the name here. So FurDev is what we've been working with, and it suggested that we create branches off of this, and then in our own sandbox. And then when we get our intrinsic working, we then do a pull request off that back into the FurDev branch. So today the intrinsic I was going to walk everyone through is the all intrinsic, and that is a simple intrinsic that will do essentially an AND comparison on a logical array. And depending on the arguments, it'll return either just a scalar, true or false, or it'll return an array of rank -1 of true and false. And rank -1 meaning that it's the rank of the input array, and it will return, if it's a two-dimensional array, it'll return a one-dimensional array, for example. So to start out with, you're going to obviously ahead of time you're going to create your branch, and then you'll come down to, I'm not in the current directory, but you want to be in this directory here. And in this directory, there's a number of files. A lot of the files that we're interested in are going to have the keyword runtime in them. And the convention has been that we try to group like or similar intrinsics together in files, and also we try to name them in a similar manner that they are in the runtime. So in this particular tab is our runtime directory, and again it's under the F18 project. It's under Flang and then runtime, and here's our runtime files. And so for the all, it's going to be located in reduction.cpp. One tip is that there's a lot of intrinsics that are already implemented in the runtime that we need lowering for. So if you're looking to jump right in, that's probably the best place to start, is to find something that's already been implemented in the runtime, and certainly you should test it out as well. Test the front end out as well to make sure the front end is implemented as well. So under a reduction here, uh, you'll see that we do have a couple of runtime routines already for all. There's two implementations. There's something that's just called all here. This prefix RT name is just it creates a prefix for our runtime, just so that we don't have any name collisions with any user defined functions. And so we have a all, and then we also have an all dim. So the main difference is that the all is a specialized routine that when you don't specialize, the user does not specify the dim, the dimension argument, that it will return a scalar, and so then in fact that's what we're doing here. We are in fact returning a boolean here. And where do I find that out? You find it out from the language specification. So it's also important to have a current copy of the language specification on hand as well, to refer to what the arguments and their meanings for the intrinsic is. And then there's this routine called all dim, which takes the dimension argument, and the main and of course it doesn't return anything, but the main difference is that we pass in, which I will talk about in more in detail in a moment, but we pass in this thing called a result descriptor, and that is that's where we store the result, and it's a descriptor, or what some people call a dope vector. You can think of it as, it's actually just a data structure that includes a dope vector as well as the value of the result. So that's all encapsulated into this thing called a descriptor. And these are defined in there's a header file, I believe, called descriptor.h. You can take a look at their definition in here as well. So yeah. So going back to the to our main directory here, for the fur lowering, Flang lib lower, there's pretty much the tutorial will walk you through the recipe, and I'll show you that in a moment here too. So the first thing I always do is, after I've determined which intrinsic I want to implement, I open up this file called intrinsic call.cpp, and this is the main sort of interface for the fur lowering. And what we do is, this is where we start to set up the arguments and so forth in this particular file. And there are a few conventions. We typically call our routines gen, followed by the keyword of the intrinsic. And so we have this so first thing we usually implement is a prototype that's local to this particular file. And so here we had created something called gen all, and it returns something called a fur extended value, which we'll talk about in a moment, and has some arguments. And these arguments are pretty much standard, are going to be standard pretty much across all the intrinsics you're going to implement. So you have a type, which I believe is going to be the result type, and then but we'll double check when we look at the routine. And then this array reference here is a list of arguments for the intrinsic, and the arguments, of course, are put into this array earlier on in the fur lowering, so they come from the front end. And then we have this. The next step is you're going to add your intrinsic to this structure called the intrinsic handler, and this is essentially a list of intrinsics and their entry points into the routine that handles the intrinsic. So here for all, we have the keyword all up here, followed by, this is actually the routine that we just created the prototype for above, and then we have a list of arguments, and the arguments are named because we do want to be able to generate keyword arguments, and then the type of arguments. So the mask is an array, and typically when you're passing an array, it's going to be an address. So we have this thing called as address to indicate that's an address. And then we have the dimension, which is going to be 1 through 15, and that's going to be as, and that's, of course, that's as value. So that's passed as value. So then we come down to, oh, the other thing I should mention too, these are all in alphabetical order. So make sure you maintain that. When we search this structure, this array essentially of intrinsics, we do perform a binary search on them, so they need to be in alphabetical order. So make sure you maintain that. And so then here's our entry point for all. And again, very similar to what we just talked about with the prototype. And yeah, the first argument is your result type, and which should be a type of Boolean value, whether that's going to be an array or just simply a scalar, and then followed by a list of arguments. And typically you're gonna want to check to make sure you're receiving the number of arguments. This is more of a sanity check. A lot of the error checking is going to be done in the front end, but nonetheless, it's a good idea, especially with FIR being constantly under development. It's good to put in some asserts and things to make sure that everything is being passed in as expected. And then we start setting up our arguments here. And so mask, we create something called a box. So we pass in this thing called builder create box, passes in the address of the array that we want, or the argument for the array, and then we go ahead and we create a box, which is going to be essentially that descriptor structure that I mentioned earlier. So it's going to be an encapsulation of the array along with the dope vector, which includes things like bounds and type and rank and so forth of the array. So the next, so then we also need to know the rank too. So this next bit of code just grabs the rank, and the specification says that mask obviously has to be an array. So we're going to have another assert there for rank greater than or equal to 1 here. And now we're going to handle the absent, the optional argument for dimension. So this is typically how we check. We have a helper function in this file that checks to see if this argument is in fact, if it's absent or present. The lowering will actually fill out, most of the time, the lowering will fill out all the arguments, even the optional arguments, and so you'll need to check whether they're present or not. And so that's what we're doing here. And if it's not present, we're going to create a default type for it. And so that's what we're doing here. Or we go ahead and grab the value, and that's what this for get base function will do. Will get us the value of that argument. And so now I mentioned earlier that there's two versions of all. There's the simplified version that returns a scalar, and then there's the other version that will operate on the descriptor or return a result descriptor. So the first time through, we're going to check whether the rank is 1 or if the dimension is absent. And if that's the case, then it's going to return a scalar. And so this next bit of code here is actually what it's doing. It's calling the gen all routine that we have defined in another file, which we'll look at in a moment, which handles and then of course we're just returning the value because it's a simple function that returns a scalar. Or if we have to call the more general routine that operates on the result descriptor, it's a little more involved. So this bit of code here, what we're doing is we're creating our result descriptor. So we have to dynamically allocate the result descriptor, and it has to be an array. So this first bit of code here that creates the result array type, we call this routine called getVar len sequential type, and variable length sequential type, which is basically array. Pass in a result type, and then recall that we recall from the specification that the result has to be a rank -1, which means that, again, if you're passing in a 2-dimensional array, it's going to be a 1-dimensional array result. 3-dimensional array, it's going to be a 2-dimensional array result, etc. And so that's why we're doing the rank -1. And then this sets up our allocative allocatable for our result descriptor temporary. And then we call the runtime routine here. Again, we have this routine called gen all descriptor that's defined later, which we'll look at in another file. And after we call that routine, we get our result value back, which is going to be in this thing called result IR box. And then this last bit of code, we actually check the value. We want to make sure that we got the expected value back. So we're expecting to get an array value back here, and so that's what this lambda is in fact doing. Otherwise, we generate an error message here. So invalid result for all is what we would generate there. Are there any questions so far? Okay. Then we can move on to the next file here. There's something called ReductionRuntime that we have. We have a bunch of different reduction intrinsics defined in this particular file. Again, the naming convention is very similar to what's already in the runtime. The runtime we have reduction.cpp, and in here we go ahead and put the name followed by the keyword runtime to distinguish that it is in fact a runtime file. So here's our runtime file, and the reason why we want to group these things separately is that there's a lot of these intrinsics actually have similar argument patterns, and so we can using templates we can exploit some reusable code, and we in fact do that with the gen all function in this case, because it's very similar to the any. In fact, the arguments are basically the same. The any is very similar to all. One does an and, one does an or logic computation. And so for the gen all, which returns a Boolean value, and again here's our return type here, which is a MLR type, and for our arguments we are going to pass in a builder object followed by a location object, and that's mostly for debugging purposes, and then we pass in this thing called mask box, which is our array descriptor that we created when we called that function called create box in the previous file, and then we pass and then followed by our dimension argument here as well. And the next step is generally we want to get our function pointer to our runtime routine, and this particular code is how we get our function pointer, and in this particular template argument will give us the actual signature for the runtime routine. So typically you're going to use this keyword mk_rt key followed by your intrinsic keyword. So in this case it's going to be all, and of course you pass in a location and builder. And since we're reusing code here, there is just a special routine that we're calling here, which I'll show in a moment. But we also want to pass in our function pointer along with the same arguments that we just received. And so we'll take a look at this particular routine at the top. It's at the top of the file. And when you look at this file, you're going to see a bunch of these routines, since there's various intrinsics that that we want to use the templated code for reusability, but certainly it's going to be different arguments and so forth. So here's that routine I mentioned, and as it turns out, this routine operates off of for three particular intrinsics. So we have all, any, and count. So these three intrinsics all have the same argument pattern, so we can use the same routine here. And as you can see, it's templated on the function name here, which is the first argument here that we passed in. So again, the code is going to be pretty much very similar to you'll find to other routines here. This recipe is pretty much what's also described, I believe, in the tutorial as well. And so we need to first get the function signature. That's what this first line does, and then we for debugging purposes we want to grab the source file as well as the source line, the line number where this in the user code where this intrinsic's being used at. So that's what we're doing there, and then we create our arguments right here, and we have a helper function that takes care of that. So you pretty much just have to fill these out. These first 3 arguments are going to be the same every time you call this function called create arguments, followed by your arguments. And the argument order is where you get the argument order is going to be in fact in your runtime routine. So again, let's look over at our runtime here. And again here, these are all, I should say, routine, and again, our arguments are going to be the this particular array. This is our mask array, by the way, the descriptor for it, followed by our source line, our source information, I should say, and then our dimension argument, and that should be mirrored as here as well. So, in fact, here's our mask array, followed by our source file and line number and dimension argument, and then we go ahead and we return our value that we get from generating this particular call here. So this function actually generates the call to the all intrinsic here. So there's that routine. That was just our specialized all routine that returns the scalar. And then now let's take a look at our routine that returns the result descriptor. So again, this particular routine uses a template that's shared between the all and the any intrinsic, and it's the same thing. Pretty much the same thing. Arguments are a little bit different because we're passing in a result descriptor here, but as you can see, we get our function pointer with a similar call, except this time we're using all dim instead of just all, and then we're just making just a call to our to a specialized or templated function here called gen reduction to args, and because we're not returning anything, we'll return things through the argument result. This function is just a void type. So we'll take a look at this particular function. At the top here. And again, this is reminder in the comments. This is for all and any, and because count unfortunately is a little bit different with its result implementation, so we had to write a different function for that particular routine intrinsic. But again, the recipe is very similar. We get our function signature, we generate our source line here. And by the way, this is the source line. You might notice that this thing called get input, this 4 has to, this matches up to the position in the like in the runtime here for where the line number lines up with the line number argument. So so it lines up there, and then go ahead and generate our create arguments like we did before, and then we just call our builder function to create the call here. And again, we're not returning anything because things are being returned in the result there. And so that's the implementation for the 2 argument reduction there. And then after I get that done, another thing I usually do is you have to create a prototype in the header file, and that's going to be located under Flang include here. And then let's go a little lower. And so here's our header files, and the convention is we name it the same as the file where those intrinsics are generated at. So in this case, reduction.h is here, which matches up with reduction.cpp. And so we can so you want to also create some some prototypes here as well. And it's just nothing, no surprises. It's just going to be your same thing as basically the signature of those routines, right? It's just no surprise here. The one thing to keep in mind, if you do create a new file for Intrinsics, just make sure you also create a new header file as well. That'll be the one thing to note here. So the next thing you do is at this point is you'd want to build your compiler, right, and make and test things, and so you will do that. You'll probably want to write some end-to-end tests just to make sure you're getting the results you expect, and then when things appear to be working as you expect, the last step is you'd want to create something called regression tests. And again, this is also described in our tutorial. And the purpose of the regression tests is to just to test the fur that we're generating and make sure that we're generating the expected fur or MIR for a particular call site. And so if we look under this directory called tests, which is under Flang, and then it's under lower. There's a file called intrinsic procedures.f90, which has a whole bunch of these tests in there. Here's the one for all, and probably looks like probably looks a little overwhelming, but if you're familiar with fur, I guess it's not. Typically you want to create versions for each type of call that you have. So in fact, for all, I created a version for just the simple all that returns a scalar, and also one that returns all the all dimension or they call the all dim here as well. So the way we create these is actually fairly simple. So for example, here's that test I was telling you about, test all.f90. This is the simple version of that test that returns a scalar. And as you can see here, it doesn't have to be a code that executes. In fact, it should just be a simple little test that just tests the call to the intrinsic. And so in this case, we have a function that returns a logical. Give it a good name that's not already being in use. So all_test works great. And then just in this case, we're just calling the all with a mask that's passed in to this function. And then using our BBC tool, you can compile it down to the MLIR, and then that will generate this particular file here. And then this is the MIR or fur that gets generated. And usually, and I'm going to go back to this file here. The way I usually start out with is I go ahead and I create this top part here. Our typically we put the name of the intrinsic. We use this keyword check label. So all these keywords check and check label. They're part of the test environment. And they tell the test environment to look for these particular patterns in the generated fur. Again, our tutorial has a link to the documentation for this particular test environment. But taking a look at some of the examples that are in this file, you can generally kind of figure out what all to do here. But I will then. So let's pull up this file real quick here.
I think we have to get to an end soon.
Okay.
Running a little bit late.
Okay. So I could just wrap it up there unless someone really wants to see it. But what I typically will do, I'll just say this. What I'll typically do at this point is is pull up the call site, and and if you locate the call site here, I usually will start with the call site and then work my way up. And these particular hard-coded variables, which are numeric, we want, because the numbers can vary, we want to create some symbolic names for them. So in this case, we create for %9, we create this symbolic name called A3, and then we also created these for %6, we create A1 and so forth. These particular arguments are ignored because those are the source line arguments, source information, and in fact, those can change as people add tests. So we want to ignore those. But other than that, yeah, I mean, it's pretty straightforward in terms of just creating just the parts of the fur that we want to test. You can leave out the parts that aren't necessary, and certainly if you have anyone has any more questions on how to do that, they can get a hold of me or anyone else who's working on the fur dev branch right now. But anyway, I think that's it. After you do this, actually, after you do all that, you'd want to run a check. So you see Ninja check Flang here to check your, and this will actually build your compiler and then run the regression tests. And here we get the expected results. It indicates there's nothing failed. There is a few things that are expected to fail, but everything else passed. So sorry about the rushed ending there. But again, if anyone has any more questions, you could certainly get a hold of me or someone else on the FUR team.
Great, thank you. I mean, we have at least one or two questions in the chat, and I have one. Do the people that posted questions in the chat want to ask them right now?
I'm also going to put my email address there if anyone wants to just send me some email.
I'll start to get the ball rolling. So you had this test generation, and then did you manually modify and create the checklines, or did you use a script for that?
I'm sorry, what was the question?
So, like at least in the Clang and LLVM IR world, we use a script to create these checklines to replace all the %9 with names and
oh, I see,
and so on and so forth.
I did it manually, but certainly if somebody if there is a script, I mean, I'd be interested in it.
Right. I mean, I thought there was one on MLR land too, but to be fair, I've never used it. But we have a fairly powerful set of scripts that does this checkline generation for Clang and IR, because at some point, once you get to like thousands of lines of these checks, you're just going crazy.
Yeah, and that makes perfect sense. The tests that we're writing for these intrinsics, because we just want to test the call, are generally going to be like three line tests, as I showed earlier. So I would think manually entering them wouldn't be so hard. But yeah, that makes perfect sense for things. And some of the other members of the FUR team here who are still here, if they are, can chime in and indicate whether they're using a script or not. But I wouldn't be surprised, since we do have some tests that are fairly long.
Johannes, you're right. There is a script in MLIR utils called generate test checks that could be used if you didn't want to manually.
Yeah, I mean the main benefit of the script, at least for me, is usually that if something changes, you kind of rerun the script, and then you get like a nice diff, because so it's not only the initial creation cost, but somebody fixed something or changed the type here or there or whatever, and now like you have 15 files that fail, and then you start typing. That's usually kind of a lot of work for little reward. Right. Okay, cool. Kelvin, you had a question. Do you want to ask that one? He might be gone. Okay.
Sorry,
I think.
I'm still here. So I just couldn't find my window.
Good.
My question is just basically if for some cases that if the intrinsic call, not necessarily the all intrinsic, some other intrinsic that occurs in the initial expression or specification expression. So I don't think not all the case you will go to the runtime. Sometimes you need to
That's
go.
correct.
So
That's
how's
correct.
that possible? Or is a different topic in this case?
Yeah. That's handled in that is handled in the front end, and
Yep.
that the tutorial does mention a little bit about that. But yeah, there are some intrinsics that are done, like you said, through the initialization data initialization or whatever that will in fact be resolved in the front end.
Okay, thank you.
Just to chime in, here's Jean from NVIDIA. Most of the intrinsic in the front end, they're folded in a machine independent or target independent way. There's an abstract representation of float integer that's used, and most are folded without any runtime, just using that. And just a few, like for the trigonometrics, ACOS and all that, then there's a runtime call made by the compiler. So we have for the math library, the compiler has access to a library and it's able to call that when needed.
So if I do the fold, if I want to fold the all intrinsic, just in this example, I'll do it in the same place and it's similar.
No, you would do it in a different place. Right now in the front end, there's lib evaluate. So it's in the tutorial.
Oh, okay.
Lib evaluate folder where you will have fold files, and you will have a case for the all intrinsics, and
it
should
got it
actually.
Thank you.
Maybe on a related note, like these intrinsic, especially kind of the math ones, but even all, the rest of the compiler, the middle end, they have some pattern recognitions for these things, right? Or special rules, like they know, I don't know, cosine of 0, and they could kind of fold that. But that only really works if it's either an intrinsic, sometimes also with the math calls, like an actual cosine call. And then there are some loop patterns that are recognized, and we potentially generate some nice code for it. Do we have a plan to kind of opt into these things, or are we saying, okay, we'll kind of do early optimization, and then at the IR level, we'll just have the runtime call? Does that make sense?
Yeah, it makes sense. So right now, when we're lowering to LLVM intrinsics or runtime calls when we're lowering to fur. And if we're getting cases where it's bad for optimization, then we'll, on a intrinsic per intrinsic basis, I think we'll be ready to add special fur operation if it turns out that that directly generating the runtime call or some inline fur is not good later to recognize some patterns.
Okay, that makes sense. Just for the record, there is a proposal out there as part of the more or less enzyme work with the automatic differentiation. But one of the things that we're trying to add is a way to annotate a function call or a function definition as an implementation of another one. So you can say, here's a definition of sign that implements actually like the intrinsic sign. And then it's basically kind of a late function call replacement scheme that might be interesting so that we can kind of benefit from the intrinsics, but in the end say, okay, if the intrinsics are not optimized away and they stick around, you can implement them back with our runtime calls, which has some benefits at the end of the day. Well, yeah.
Interesting, and we'll work with attributes, I guess, LLVM attributes.
Right. Yes.
Okay.
So it's not yet passed. So we proposed it. There were some comments, but general agreement that is necessary. For one, on the GPU world right now, we actually are not able to use LLVM intrinsics for math or other things. Like if you use an LLVM sign in a GPU code in LLVM right now, at least for NVIDIA GPUs, you're pretty much out of luck. and that is kind of unfortunate. So this is kind of our way to use LLVM sign and later on replace it with an NV sign intrinsic. As opposed to teaching all of LLVM that an NV sign intrinsic is the same as an LLVM sign intrinsic. Okay. But we can revisit this once that actually made it in, and then we'll see what form actually made it in. Feel free to comment on the thread if that's of interest. Okay, everyone, we're 15 minutes over.